Hi, I'm Christoph from Berlin, Germany, and I work for KDAB. In this series, I talk about how to speed up your embedded development experience. Through your comments on social media, we got a lot of feedback for our video on bundling. Some of you found the topic of nightly releases relevant to their daily work, so I will show them in action. In my case, I will show you my Yocto build system on my Linux build server. Here I'm already on my build server. This is not my laptop because we prefer to use Yocto on a build server. Actually, most of our Yocto builds are run on servers for two reasons. First, we have a powerful build machines that can produce an image in minutes rather than in hours. This machine is actually optimized on single-thread performance. That means non-parallel jobs run faster here. Also, the server is up 24/7 and can build in the night. If I would use my work computer for this, I would not have a great time. So that's why you find these beefy machines everywhere where you can find Yocto. First, I will kick off a Yocto build by hand. It will produce an image for me containing the latest version. That means BSP, drivers, operating system, start scripts, and the applications I wrote for the customer. These all form the partitions that will exist on my device. But an image in that form might only be suitable for SD cards and are complicated to flash with other methods. What we want is an over-the-air update, OTA update. For this, we need to create a new image that is now usable in an automatic updater. For the updater, I'm using one of the most common ones, swupdate. It is open source and you can find it on GitHub. There are more examples for updaters such as Mender, Rauk, which are partition-based, just like swupdate. Or there's OS3, a famous example for a diff-based update. But for this example, we will use swupdate. So when creating such an swupdate image, one needs to wrap this created system partition and provide some additional information. In Yocto, you need to specify the name of the image you want to wrap. So here I'm where I have all my images for my Yocto build. You will find the Speidelverwendmeister swupdate.bb, which is the big bag file for the actual image. When we look inside, we will see that it contains all the important information for the image. For example, the kernel, the U-boot, and everything that is actually a part of the image. That is our original Yocto image that we want to wrap. Now I created a new image, which is now called Speidelverwendmeister SWU, just the SWU file. And if we look inside here, we will see this is actually the wrapper for our image file. This will reference the swupdate images, the Speidelverwendmeister swupdate image that we create previously. So we take this wrapper image and create a new over-the-air updatable image with the help of swupdate. But there is more important information contained in this swupdate image file that I've just shown you. The two most important lines are these two. There's SW description, which will show us the partitioning scheme in our image. So the boot and root partitions, and we will look into this soon. The second one is update.sh. This is the script that actually runs the update, so actually writes all the information to the disk. So let's first look into the SW description. Here you can actually see the individual files that will be written as partitions onto our overall image. You will see there is here an image, and this will again reference the update.h doing the actual flashing. We will see it's a normal, regular bash script that will determine the root partitions and we'll switch them accordingly. More about this in a second. And we'll get the current root device, get an update device based on that, format the update device, and then do the actual update. This script is possible to be extended so that you can run additional steps before or after the update. Let's talk about partitions, which are so important in embedded devices. On the right side, you can see the flash memory of our device. This flash memory contains many partitions, for example, the boot partition. The boot partition contains the kernel, device tree overlays, which are important for hardware compatibility, and it tells the bootloader where to start the kernel from and which root partition to start from, where our actual data, our images, and all our applications are actually in. Then I said there's at least one root partition. In this case, I called it root partition A. There might be a second root partition B, and sometimes we have a recovery partition. There is a very famous fallback scheme that many embedded devices use. It's called A-B-Fallback Scheme or A-B partitioning scheme. So when we produce the device for the first time, we set the boot partition such that it always starts from the A partition. So our application just normally is in A partition and starts from the A partition. But let's say we are having an update now. This update is now detecting that we are working from the A partition and selects the B partition as the new update device. So the update will happen on the B partition. At the end of the update, when it was successful, we set the reference of which image we want to start, which partition we want to start, to the B partition. Now we are running this new image, this new B partition with our latest software. In the boot file system, there is a little counter. And this counter is always counting up on every boot. It is the responsibility of the partition B, or our root partition, to reset that counter to tell the boot partition that everything went well. So it's setting it to 1, then it's setting it to 0 again, for example, because everything went well on the B partition. Let's say there is an error. There's something not going well with our update and our B partition is actually not working. Here, the boot counter will increase more and more and more, and when it reached a certain count, for example 3, it will switch back to the A partition, which we know was a good partition to be updated from. So we know this is a good partition. Let's say there's still something wrong, and then the boot counter might increase even further. With this, the partitioning scheme might switch to a so-called recovery partition. This is not the full image. It doesn't really contain all the applications. It mostly only contains a single updater, which can then rescue the device or set it back to factory mode. In this way, we are always safe with our updates. So while the last part was on reliability of your images, there's also parts that enable security, which is signatures and encryption of images. Let's start with signatures. An image signature is what I consider most important for images created for over-the-air updates. They form a special signature over the whole contents of your image, and devices only accept those signed images to be installed. This means no one can change the contents of the image, and this pushing malicious code in wrong updates to your customers. Only the vendor can produce updates here. Image encryption, on the other hand, I would consider a bit less important. It only safeguards the specific information that is within the image. So your secret code, your secret source for your application. That means no one can look into this image and find out what you're actually calculating in your software. So with this all configured, we can now build our SW update image. So I just write the normal built-in update for my target Fermentmeister here, and it will build the image for us. we will get out the final SW update image later. Now that we can build the image every night, we need to make sure that it's automatically run every evening to produce a new nightly for us. For this, we will use systemd services and systemd timers, which is the modern way of doing it. So here I have a systemd service called nightly.service, and we are looking to this first. We have a little description, builds the system image every night. It wants a timer that is existing. It is of a one-shot type, and it starts our build and update script, which then produces the image for us. And to install it, we need to have this line as well, that it's wanted by multi-user.target. Associated with this is also the nightly.timer. And this now also has a description. It requires the service to be existing, and it is running the nightly service on the calendar date every day at 23:30. With this, we are making sure that every night we have a fresh image that we can install the next day. This will make Yocto run every night. So what comes out of Yocto is a ready-made image, but it is still on the server, so the script that I built around it contains a part that is uploading it to our firmware server. Our version is uploading it to a simple web server, but there's also hosted services such as Mender, our partner, which hosts the firmware for you. But also Toradex does this with their Horizon product. The installation part is up to you. Either your developers install the nightlies on the devices by hand every day, or the devices are set up in a way they install the nightlies when they know there is a new one. This can be done either by a timer every morning before you enter the office, which is simple, but it works great in development, or by being notified about a new update, which basically means that the device asks with a timer again for a new update every 10 minutes and is notifying the user in that case. So here you can see the web installation process. Every time you use SW update, you always will get a web installer as well. So I just logged into the IP address of my device with the port 8080, and this opened this nice web page for me. In this web page, I can upload firmware files, which I will now do. I will browse my firmware files, and I will select the image I want to install. This is now taking some time. First, it's uploading the image to the device. And when this is done, it will update the actual device, which I will show you in a second. So as you can see, having nightlies is just writing some scripts around your build process. In this video, I showed you how to achieve this with Yocto Linux images, but I'm sure you can adapt this easily to your own build processes. I made this video because some of you asked in the comments. If you have more questions about some of our videos, let us know, and we'll try to produce a short explanation video such as this one. Until then, see you in the next one, goodbye and auf Wiedersehen.